Assalamualaikum everyone. In today's physics episode, we tackle one thermodynamic process known as adiabatic process. What do we mean by the title of this video? Adiabatic heating and cooling. To find out, just stick around till the end of this video. Watch and learn. The key concept applied in this topic is in an adiabatic process, there is no heat flow into or out of the system. So, capital Q is equal to 0. And the internal energy equals the negative of the work done by the system. That is, delta U is equal to negative W. If the system is an ideal gas, the temperature capital T, volume capital V, and pressure P all change in the process. But the quantities T times V raised to the power gamma minus 1 and P times V raised to the power gamma remain constant. Gamma is the ratio of specific heats for the gas. Question number 1. A quantity of argon gas with heat capacity C sub B equal to 3 halves of the gas constant capital R and heat capacity C sub P equal to 5 halves of the gas constant big R is at the pressure 4.00 times 10 to the 5th Pascal and occupies volume of 2.00 times 10 to the negative 3 meter cube. Then, the gas expands adiabatically to a new volume of 6.00 times 10 to the negative 3 meter cube. Calculate, letter A, the value of the constant gamma for argon. Letter B, calculate the final pressure of the gas. And letter C, calculate the work done by the gas as it expands. So for our solution, let us first identify the data given in the question. We have the heat capacity at constant volume. This is denoted by capital C sub V. That is equal to 3 halves times the universal gas constant capital R, and also the heat capacity at constant pressure denoted by capital C sub P, which is equal to 5 halves times the universal gas constant capital R. We are also given the initial pressure P sub 1 equal to 4.00 times 10 to the 5th Pascal. Likewise, the initial volume of the gas V sub 1 equals 2.00 times 10 to the negative 3 meter cube. And the final volume V sub 2 equal to 6.00 times 10 to the negative 3 meter cube. And our target variables are, letter A, the constant gamma, which is the ratio of constant C sub B over C sub V. All right. The second target variable is the final pressure P sub 2, and letter C, all right, we are also asked to find the work done by the gas as it expands. And we will be applying the following equations for our computations, all right? So the first one is how to find the constant gamma, all right? So gamma is just equal to the ratio of the heat capacity C sub P divided by the heat capacity C sub V. And for question letter B, we can find the final pressure P sub 2 by multiplying the initial pressure P sub 1, uh, quantity, all right, B sub 1 over B sub 2, raised to the power gamma. And lastly, for the work done W, we'll be using the formula W is equal to the heat capacity C sub B divided by the universal gas constant, and that will be multiplied by the quantities inside this open and closed parentheses. That is the product of P sub 1 and V sub 1 minus the product of P sub 2 and B sub 2. Take note, we will be applying the rules of significant figures in all our succeeding computations. So moving on now to our computations, starting with letter A, computing the constant gamma, all right, using this formula. So you substitute C sub P is equal to 5/2 of the universal gas constant, capital R, divided by C sub V, which is 3/2 times the big R. All right. So notice that the big R can be cancelled, and we will get the value of gamma simply equal to 5/3. For the second question, finding the final pressure P sub 2 using this formula. All right. So substituting, we have the initial pressure 4.00 times 10 to the fifth Pascal, and that will be multiplied, all right, by the ratio of the initial volume to the final volume, and that ratio inside the parentheses will be raised to the power 5/3. So doing our math, all right, we first get the result of dividing, all right, V sub 1 by V sub 2, all right, and that comes out as 1/3. So using your cycle, we can determine uh, the value of 1/3 raised to the power 5/3, and then that will be multiplied by 4.00 times 10 to the 5 Pascal. That is our final pressure P sub 2 equals 6.41 times 10 to the 4th power Pascal in 3 significant figures. For the work done by the gas as it expands, we have W equals uh, the constant C sub V divided by the universal gas constant R, right? That is 3 halves times big R divided by the same big R, right? And the result of that is the number 1.50, right? Uh, or 3 halves, because the constant capital R cancels out. And then uh, the result of multiplying P sub 1, V sub 1, right, which is 4.00 times 10 to the p Pascal times 2.00 times 10 to the negative 3 meter cube, all right, the product is in fact equal to 800 point joules, meaning in 3 significant figures, while the result of multiplying P sub 2 times V sub 2, or 6.41 times 10 to the 4th power Pascal times 6.00 times 10 to the negative 3 meter cube, all right, their product in fact is equal to 385 joules, right? And these two quantities, all right, will be subtracted, and then the result will be multiplied to 1.50. That is, we get the value for the work done equal to positive 623 joules, also in 3 significant figures, all right? This means that the amount of work done by the gas as it expands is equal to positive 623 joules. And we can evaluate our answer by citing the first law of thermodynamics, right? So this positive work done by the gas is just equal to the negative delta U, or the change in the internal energy. And since the process is an adiabatic expansion of the gas, where the amount of heat transfer or heat flow, capital Q, is equal to 0. So transposing delta U and W, okay, we can say that the work done is equal to the negative of the change in the internal energy delta U. So what does this imply? A negative delta U implies that the temperature, the gas, decreases as the gas expands or does work on its surrounding. So this is what is meant by the term adiabatic cooling, all right, as suggested by the title of our episode. So adiabatic cooling is one where the system's internal energy decreases not by liberating thermal energy, but by doing work on the environment. All right? So the system or the gas is doing work on its environment or surrounding. All right? So the result is a decrease in the internal energy of the gas, which is also associated by a drop in its absolute temperature. Our last question, number 2. A quantity of oxygen gas with heat capacity C sub V equal to 5 halves times the universal gas constant R, and C sub P equal to 7 over 2 multiplied by the universal gas constant, big R, is at absolute temperature 325 Kelvin and is under pressure equal to 1.00 times 10 to the fifth power Pascal and occupies volume of 6.50 times 10 to the negative 3 meter cube. After you compress this gas adiabatically, its absolute temperature is 855 Kelvin. Questions are: calculate letter A, the value of gamma for oxygen. Letter B, calculate the final volume of the gas. Letter C, calculate the final pressure of the gas. And letter D, calculate the work done by or on the gas as it is compressed. Identifying the given quantities, we have 5 halves times the big R for the constant C sub V, and 7 halves times the big R for the constant C sub P. All right. So we are talking about oxygen gas, which we know is a diatomic gas. Now, the initial pressure P sub 1 is also given 1.00 times 10 to the fifth power Pascal. And the initial temperature equal to 325 Kelvin, and the final temperature T sub 2 equal to 855 Kelvin. Likewise, the initial volume of the gas B sub 1 is given also as 6.50 times 10 to the negative 3 meter cube. And we are asked to find the following. All right. The constant gamma, the final volume B sub 2, the final pressure P sub 2, the work done by or on the system, and lastly, all right, the formulas or equations that we will be using for our computations. As usual, for finding the constant gamma, that's still dividing C sub P by C sub V. In finding the volume, B sub 2, we base it on this relationship of the ratio of the volumes V sub 1 over V sub 2, all right, with the ratio of the temperature, absolute temperature T sub 2 over T sub 1, all right. So the ratio of V sub 1 over V sub 2, okay, is raised to the power gamma minus 1. And for finding the pressure P sub 2, we also relate it, all right, to, of course, P sub 1 and the ratio of V sub 1 and V sub 2, each raised to the power gamma. And for the work done, W, we use this formula, all right, which is getting the reciprocal of gamma minus 1 and then multiplying it by the values inside this parentheses, the product of p sub 1 and v sub 1 minus the product of p sub 2 times v sub 2. Moving on to our computations, for the heat capacity ratio gamma, we have gamma equals 7 halves times R divided by 5 halves times R, and cancelling big R, we get the value of gamma equal to 7 over 5 or 1.40. And for question letter B, all right, before we'll find the value of V sub 2, all right, using this equation, we first determine the ratio T sub 2 over T sub 1. That is 855 Kelvin divided by 325 Kelvin. So their ratio is equal to 2.63. And that number 2.63, all right, is also equal to the ratio of V sub 1 over V sub 2 raised to the power gamma minus 1. All right, gamma minus 1 or 1.40 minus 1 is 0.4. All right, so what we want is to isolate V sub 2 in this equation. All right, so what we do is to also raise the whole thing, including 2.63, all right, to the power equal to the reciprocal of 0.4, which is 2.5, all right, because 0.4 is the same as 4 over 10 or 2 over 5, and the inverse of 2 over 5, of course, is 5 over 2, which is 2.5. All right? So now, we were able to isolate B sub 2, which is simply equal to the initial volume B sub 1 divided by, all right, the number 2.63 raised to the power 2.5. So, substituting the value of V sub 1, which is 6.50 times 10 to the negative 5 meter cube, and dividing it by this number 2.63 raised to the power 2.5 with the help of our scientific calculator, we will get the value of the final volume B sub 2 equal to 5.79 times 10 to the negative 4 meter cube. So, as you can see, this volume B sub 2 is lower than the initial volume B sub 1. All right? Because in this question, we are talking about the process of compressing the gas. So when the gas is compressed, all right, we expect its final volume to be less than the initial volume. For question letter C, computing the final pressure P sub 2, all right, using this formula, we have the pressure P sub 1, 1.00 times 10 to the 5th power Pascal multiplied by the ratio of the volume V sub 1 over V sub 2 raised to the power gamma, that is 6.50 times 10 to the negative 3 meter cube, all right, that is to be divided by 5.79 times 10 to the negative 4 meter cube, and then the ratio is raised to the power 1.4. So doing our math, all right, we first get the value of the ratio V sub 1 over V sub 2, and then raised to the power 1.4. And that number will be equal to 29.5. So we multiply that by p sub 1.00 times 10 to the fifth power Pascal. So we get the final pressure p sub 2 equals 2.95 times 10 to the 6th power Pascal in three significant figures as well. And last but not the least, we compute the work done W using this formula. That is, the work done W equals the reciprocal of gamma minus 1, which is 2.5. And then that will be multiplied by the number inside these quantities, or p sub 1 minus p sub 1 times p sub 1 minus p sub 2 times p sub 2, or 1.00 times 10 to the fifth Pascal times 6.50 times 10 to the negative 3 meter cube, then minus 2.95 times 10 to the 6 Pascal multiplied by 5.79 times 10 to the negative 4 meter cube. All right. So again, simplifying, all right, the result of multiplying p sub 1 and b sub 1 is 6.50 times 10 to the second power joules, while the result of multiplying p sub 2 and v sub 2 is 17.1 times 10 to the second power joules, since our formula says that p sub 1, v sub 1, all right, or p sub 2, b sub 2 will be deducted from p sub 1, b sub 1. That's why we have here the minus sign. All right, so the difference is to be multiplied by 2.5. That is, our final answer for the work W is equal to negative 2.65 times 10 to the third power joules. So it's a negative work, meaning that the surrounding, or according to the question, it was you who did the work, all right, when you compress the gas. All right, and for our evaluation, in this adiabatic compression process, the negative work, all right, is equal to an increase in the internal energy of the gas. All right, that is according to the first law of thermodynamics, where big Q is equal to 0. All right, and we will get the relationship between the work done W and the change in internal energy delta U. That is, the work done is equal to positive delta U. All right? So, in this adiabatic compression, uh, the negative work, all right, is equal to an increase in the internal energy of the gas. All right? An increase in the internal energy of the gas because delta U is positive. And this is also associated to an increase in the temperature of the gas. All right? And the title of this episode, adiabatic heating, simply means that we are increasing the internal energy of the gas, or that is also increasing the temperature of the gas without any heat transfer big Q, which is equal to 0. So no heat transfer, no heat flow, but we are able to increase the temperature of the system or the gas. That is what was meant by the title adiabatic heating. So that concludes my tutorial for this topic. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.